Hello everyone. This topic for the lecture is clean chemistry for environmental sustainability, and the speaker is Dr. Lim from Singapore Institute of Technology. Now, the time it's yours, Mr. Lim.
Thank you very much. Thank you everyone for joining me this afternoon. Today I'm talking more about green chemistry for environmental sustainability. So what you will learn from today is what is green chemistry and also the 12 principles of green chemistry. So what is green chemistry? So it's defined, green chemistry is defined as a multidisciplinary field involving fundamental science, business, law and engineering. Sometimes green chemistry is also known as green engineering, environmental design, sustainability, industrial ecology as well. So we also like to know what is sustainable development in a way, and is being defined by United Nations as meeting the needs of present without compromising the ability of the future generations to meet their own needs. So the objective of today's online lectures is to understand what is green chemistry and to appreciate the general concepts of green chemistry and its applications in the chemical industry. So in the past, what happened is that basically when we look at productions, especially in chemical productions, we are looking at trying to get as much yield from the feedstock of the chemicals of itself. And we understand that this process is not sustainable. And in presence, what we have to deal with is, besides looking at the use, we have to look at how we can optimize the feedstocks, the kind of feedstock that we have, how can we be compliant to the law that government, the industry, and how do we dispose of the waste if it's being produced as a byproduct of the production processes, the liability of the productions company as well, and to treat the waste if they are not deemed not to be safe to be disposed in the environment. And here we also understand that in the 21st century revolutions called green chemistry is a reactions to the environment and economic costs that often are in the dark. So these are things that we do not are not taken care of in the past, and therefore we have to now look at this issue seriously, so that we can look at productions that will make the environment sustainable in the future. So here again, what is green chemistry? Green chemistry is the utilization of a set of principles that reduce or eliminates the use of generations of hazardous substance in design, manufacture, and the applications of chemistry products itself. There are various tools that we can make use of, such as looking at alternative feedstock. For example, nowadays we are looking at fossil fuel most of the time, crude oil, as one of the main feedstock to our chemical industry. So how do we look at the use of renewable new raw materials in future? And also look at alternative reagents as well. How can we make the reagents more bio-based from bioproductions that is more sustainable compared to the using of natural resources today itself that is depleting? How we look at alternative solvent. Basically today in chemical productions we are looking at using organic solvent. So the organic solvent are usually toxic, flammable, and not very safe to use. And if you are able to come up with a synthesis method that use, for example, water as the solvent, that will make the chemistry or the productions much more sustainable and safer to produce the goods that we are, the final products that we want to produce at. We also can look at alternative products that are of the same usage as what we are using today, but are less or non-toxic products itself, so that it will not harm the environment. As we have looked at previously, when we look at gases used in refrigerators, these are greenhouse gases that is being used, and today we are trying to minimize such usage of greenhouse gases in the products itself. And using of alternative catalysts is another way. Catalysts, we know that will help to speed up the reactions and also make the conditions of the reactions milder, and therefore that can help in terms of using less energy in the production itself, especially if you are able to use solid acids, for example, or solid base catalysts, and that also help in the way that you will reduce the separation process and therefore the energy that being used to do the separation subsequently between the reagents and the products. And we also can use process analytical chemistry and tools to monitor the reactions as they proceed, so that we will know in time if a production is being run in the correct way, and if it's a runaway reactions, we can try to minimize the waste that is being produced along the way, and therefore that helps in cutting down the amount of waste being produced unknowingly if we do not have such process analytical tools to monitor the productions. And the need of chemistry, green chemistry itself, basically chemistry has improved our life. Life expectancy has increased tremendously over the years, from 50 years of a normal human being in the 1900s to 75 years old for a person in the living in the 1990s. And for example, in today's Singapore, we are looking at us having a life expectancy of about 82 to 83 years old. And this has been done by through the knowledge of chemistry, so this through the improved access to healthcare and development of pharmaceutical drugs itself, and also our knowledge in terms of water purifications, and therefore that lead to increase in terms of hygiene level in our society, and therefore that helps in the our lifestyle as well, and also in terms of food preservations by knowing more about the chemicals being used that help to make the food safer for our consumptions, and to also the improved packaging of the food by polymer allow the food to be kept or to be preserved for a longer period of time, and can also be shipped to or passed on to people staying at the very remote areas, and therefore allow food to be accessible to many people, and that again help to improve our lives itself. The green chemistry also has helped to produce polymer. So these are materials that are stronger, lighter, that can be used in vehicles itself. It helps to save energy and also help in our daily transport, and therefore improve our life itself. And also in temperate countries, it can help in terms of insulations for homes itself, and basically that also help in a way to manage the amount of energy that is being used for heating or cooling of homes. So increase of awareness over the past 30 to 40 years that modern processes are not always compatible with maintaining a sustainable environment, and therefore we need green chemistry today to help to keep or maintain a sustainable environment for our future. For example, in the early days, the pollutions can really lead to environmental disaster. So here is an example of a river, Cuyahoga River in Cleveland, Ohio, in the United States. So this happened in the late 1960s itself. So according to the Time magazine, as can be seen from the illustrated here, so some river, chocolate browns, oily bubbling with subsurfaces gas. So it actually oils rather than flow, and anyone who falls into the river does not drown but decays. That shows the amount of waste and chemicals that are being dumped into such river. So there are many things being dumped into river, such as gasoline, oil, paints, and metal. So sometimes they also call the river as a rainbow of many different colors. It may sound attractive, but it's a hazard to everyone that stay near the river itself. And eventually, on 22nd of June 1969, fire erupts on the river several times, and this river fire actually captured the national attention when the Time magazine reports it, and therefore that leads to changes for the country as well. As more people are aware of such incidents, they want their environment to be more safe for their lifestyles, for them to live in, and therefore there is a need for green chemistry. And we know that there's many costs to waste itself during the productions. So basically there's a cost to waste when we do not practice green chemistry. We know that when waste is being produced, first of all, we need to dispose of the waste, and therefore that increase the production costs, because basically additional costs will have to be put in itself. And since some of the raw materials are being used to produce such waste during the production processes, what does it mean is that the raw material usage is not optimal or is inefficient, and therefore it leads to the generations of byproducts. And when these byproducts are classified as waste, it also leads to energy inefficiency, because energy is, besides being used to produce the products that we are interested in, is also being used to produce the waste as a byproduct. And there's also cost to the environment as well, because we use more energy. Most of the energy that we are using today are from fossil fuel, and when we do not use energy efficiently, it means that we lead to more emissions to the environment, and that lead to pollution as well to the environment that we are staying in. And you can see that nowadays there's a cleanup cost that is associated with that, with basically emissions lead to problems, issues with the residents staying near the facilities, and there's a cost to clean up such pollutions. And today's people are proposing carbon tax, for example. It's one of the ways to bring awareness to such manufacturing plants and to tax them in a way so that they can recover some costs to help to clean up the pollutions that is being done by such companies. And companies will also have to deal with public relations, so that with more awareness of the pollutions they are conducting, or they are affecting the neighbors, and basically they need to pacify the attitudes of people staying around the production plant. And therefore, if it's deemed as a industry that is not clean, produce pollutions, not safe, and that can affect the attitudes of workforce, that means that you have to pay more to get workers to work for the companies. And basically that also lead to tougher law, because we want to prevent pollutions. There will be more stringent laws that kick in. For example, in some countries, there are requirement of ultra low sulfur diesel itself. For example, basically, for example, in Europe, they have this Euro 6 standards. So that is some of the law that can kick in to make it more stringent in terms of the products, and therefore making the productions much more expensive. So there is an increased cost of technology to stay in business because you need to meet the new law that is being set to preserve the environment. And there's a cost to the future as well, because if we are using raw material, natural raw materials, therefore we are using up these natural materials over times. For example, like fossil fuels, so they have a limited lifespan, and therefore in future, or our future generations will not have a chance to basically use such raw materials anymore. So for green chemistry, basically there are many usages itself. One of the major uses is the energy. In the energy sectors, in areas that lead to global changes, in terms of resource depreciations, in terms of food supplies, and basically in toxics in the environment. How do we reduce the toxics in the environment? And these are done through various methods. So for example, energy, the vast majority of energy generated in the world today is from non-renewable sources that damage the environment. So not only that by harvesting the raw materials, it lead to pollutions in, for example, oil. You try to dig oils and coals itself. These are very harmful to the environment. By burning this fossil fuel to produce energy, it also produces carbon dioxide that is a greenhouse gas. It also produce pollution such as sulfur dioxide, nitrogen dioxide that also harm the environment by that can cause acid rains itself, and also other compounds that are toxic to the environment. And therefore, by using the fossil fuel, it actually can also lead to other greenhouse effect itself. So green chemistry will be essential in developing the alternative source for energy itself in terms of generations, such as looking at solar cells, looking at hydrogen fuel cells, looking at bio-based fuel as well, as also to in a way to continue the pathway towards energy efficiency, like looking at using catalysts and products design at the front of the productions. So before productions, we'll look at how to leverage on catalysts and how to design the processes so that we can optimize the energy usage. We can also about global changes. Nowadays, we are very familiar in terms of the concern on climate changes. In terms of, for example, even in terms of global distillations, that's the transport pollution from warmer to colder regions in the globe itself. This can be addressed through the development and implementation of green chemistry technologies. So in terms of resource depletion itself, so due to the over-utilization of non-renewable resources, natural resources are being depleted at an unsustainable rate itself. So fossil fuel, again, is essential issues. So renewable resources can be made increasingly via technological and economically through green chemistry, such as the productions of biomass, making use of nanoscience and technology in terms of energy or usage as well, in terms of how we produce our solar panel to leverage on this solar energy, how we can recycle carbon dioxide to become a raw materials itself. How we can use bio again chickens, how to use bio-based materials to replace as a raw materials for today's fossil fuel being used as a raw materials, and how we can look at the utilization of the waste being generated from the processes itself, and how we can recycle this waste so that we can make them into useful products, and therefore the waste that are being produced as a byproducts are not no longer a waste in the productions. And in terms of food supplies, you can see that while current food levels are sufficient, distributions is inadequate. That's why there are people that can go hungry without food because there's a very poor in terms of food distribution network. So we also know that the agriculture methods are not sustainable. Future food production intensity is needed as well. So green chemistry can help to address tackle the food supplies issue. So green chemistry is about developing pesticide, for example, which can only target at certain organisms that we want to treat in and to degrade to harmless byproducts in the environment after it's being used or after its intent usage. That is something that is in the pipelines and something that we need to do so that the pesticides, beside doing the goods in terms of targeting at organisms that we are interested in, but also targeted at the environment that is happening today, and therefore it's not sustainable. And also green chemistry is also about developing fertilizer that is effective and designed to minimize usage as well while maximizing its effectiveness. So it's not the application of fertilizer all over the plantation, for example, but fertilizer that you have low usage but while maintaining the effectiveness of the current fertilizers. And methods of using agricultural waste for beneficial and profitable uses as well, to look at how we can recycle this kind of biomaterial or biomass in terms of producing products, useful products, or looking at it being used as a raw materials for products or for energy itself. So toxics in the environment, substances that are toxic to human, the biospace, and all sustainable current things are currently being released at the cost of life, health, and sustainability of the future. So one of green chemistry greatest strength is the ability to design for reduce hazard or design for safety, whether to design the processes to be safe itself in terms of the productions and for the products to be the safe for the environment as well. So there is a various approach towards preventing pollutions. So one is at the topmost is preventions. As we know that prevention is always better than cure. So at the topmost, we are looking at preventions and the reductions of waste. And sometimes we understand that the production of waste cannot be avoided, and therefore we need to look at how we can recycle and reuse this waste so that they are no longer being produced as a waste, but they can be used as a useful products. And if these are not possible, and if these wastes are actually harmful to the environment, we need to look at how we can treat these byproducts or these wastes so that after the treatments, they are safe for the disposal into the environment. And we know that green chemistry is not a solution to all environmental problems, but the most fundamental approach to preventing pollutions. So I'd like to introduce another concept called the inherent atom economy as a tools for green chemistry as well, and as tools to try to prevent the productions of waste. So atom economy is a way to measure the atom wasted when making chemicals. So the higher the atom economy, the greener the process. 100% atom economy means that all the atoms in the reactants have been converted to the desirable products. That means all the atoms that appear in the reactants also appear in the products, and therefore there's a 100% utilizations. And there are certain reactions that are basically more atom economics itself, and there are certain reactions that I'll talk or examples that I'll give later on that demonstrate that it's an uneconomic reaction itself. So for example, a rearrangement reactions, addition reactions, Diels-Alder reactions, and other concerted reactions are normally grouped as atom economic reactions. We look at some example subsequently, and for example, the atoms uneconomic reactions, we are looking at substitutions. That means that when we have substitution reactions, we'll see that some of the atoms will be substituted and therefore will appear in the waste. We look at eliminations, that means part of the molecules will have to be cut off and therefore will end up as a byproduct or waste of the reactions. And we look at other reactions like Wittig, that is, you need to produce waste that is of high molecular weight itself, and Grignard reactions. So let's look at some of the examples. So many rearrangement reactions occur on heatings, and therefore it is definitely 100% atom economy. And we can see from this reaction, the Carlson reactions. So by heating it, basically the molecules undergo a rearrangement reactions. So all the atoms that is being used in the reactants also end up in the products. So here, what we can see is that this kind of reaction is definitely desirable because there is no waste being produced as a byproduct. And to optimize such reactions, we need to look at how we can further influence the rate of reactions. And for these reactions, you can see that these are partially charged, and therefore the solvent polarity will be important. And we also can look at how reactions is 100 times faster in water than methanol for certain reaction itself. And therefore, for such reactions, we can see that by using a right solvent and more safe solvents, we can even increase the productions of the reagent. So in terms of addition reactions, we can see that here we are looking at hydrogenation reactions, where benzene ring is hydrogenated with hydrogen gas via a catalyst, and again all the atoms being in the reactants are end up as the products, and again this can achieve a 100% atom economy. And so are the other addition reactions that we can see here. So here again, adding bromine to the reactants here, alkenes here, and therefore you can see that all the atoms that appear in the reactants end up in the products, and therefore it's 100% atom economy reactions. When we look at concerted reactions in this way, the special reaction of Diels-Alder reactions, whereby you add a dienes to a alkenes itself. So it's an excellent way of forming two carbon-carbon bonds simultaneously. So this concerted mechanism, so is highly stereoselective itself. So some Diels-Alder reactions can be carried out in water or ionic liquid as well. So which can also sort of act as a catalyst. You can see that for such concerted reactions, again, it's an addition reactions. All the atoms that are appearing in the reactants end up in the products, and therefore it's a very atom economy reactions. And in contrast, let's look at Wittig reactions. So these are very good methods to prepare alkenes with double bonds at a specific location that you want to, and basically you are reacting alkyl halide with ketones, for example, so that aldehyde for these reactions, so that you can specify where the CC double bonds are being formed, and these are being used. This reaction can give high use and take place under very mild conditions. And most of the time, when we are manufacturing vitamins and pharmaceuticals, we need to make use of these reactions. But we can see that this is not a atom economy reactions. Basically, when we look at the products or final products, we have the what we call the triphenol phosphine oxide or TPPO that has a very high molecular weight of 278 itself. And beside that, we also have other wastes that are less harmful, for example, sodium chloride and water itself. So again, you can see that the TPPO having a molecular weight of 278, which is much heavier than the products itself, can make the reactions not atom economy itself. And how do we do that, right? Because from the hierarchy of waste of green chemistry, we look at the first part is that we try to prevent the production of waste. And in this case, if you are going to use these reactions, this waste is unavoidable itself. We cannot avoid production of this waste. So we go to the second step. We look at how can we reuse basically a TPPO, right? So in this way, we need another set of reactions that will convert the TPPO back to TPP for reuse. That means that we want to convert it to TPP here so that it can continue to reuse these byproducts itself. So here, that's how we do it. These are reaction schemes. Again, we can see that it's not all free itself. That we still have some byproducts. We still produce carbon dioxide. We still produce this chemical here. But what happened is that we are producing slightly less waste. So, and we can recycle the main bulk of the waste here, TPPO, back to the raw materials, and therefore making the overall reactions greener. So atom economy is definitely one to look at, one of the concept to look at for solutions to green chemistry. So wherever possible, consider using atom economics reactions, and also consider using reactions parameters such as U, reaction conditions, number of steps, ease of preparations, nature of byproducts and solvent itself into considerations. If reactions has poor atom economy, we need to try to minimize the effect by, for example, looking at careful choice of catalyst, in-process reuse or recycle of the byproducts itself that is being used, and to ensure that the byproducts are harmless to the environment if eventually we need to dispose of it. So with that, you need to another concept as what we call the ideal synthesis itself. So for ideal synthesis, definitely it must be atom economy or atoms efficient itself in terms of usage. What we look at is basically what happened, what appear in the reactants. Most of them have to appear in the products. And when we look at the example earlier on, normally when we achieve a high atom efficiency, the reaction scheme is very simple. It can be a one-step reactions, right? Or it has to be simple. If not, we have to go through many steps. That means that more energy will be required. And we'll look at high U, if possible 100% U for ideal synthesis itself. If you are able to do so, we look at reactants that are from available materials so that we do not need to go through unnecessary synthesis steps to obtain the raw materials for the synthesis that we want to for our products. So it has to be environmentally acceptable, be it in the solvent or in the reactants and in the products as well. And hopefully we can always also recycle the solvent, for example, so that there's no waste to the reagents and overall the reactions can be safe. With that, I would like to pause for a moment to take some questions. Is there questions?
Hello everyone. If you have question, please unmute your microphone. Okay. Maybe you can continue, Mr. Lim.
Okay, thank you very much. So let me proceed with the second part of the lectures itself. So besides looking at atom economics as some of the concepts and ideal synthesis, I'd like to introduce the 12 principles of green chemistry itself. Again, the first principle is prevention itself. We always know that prevention is better than cure. So if we don't produce waste, that means that we do not need to spend much effort in terms of trying to treat the waste, recycle the waste, and dispose of the waste subsequently. And atom economy is the concept that is being introduced previously, and that definitely is one of the principles of green chemistry because that helps in terms of measurement of how efficient we are in terms of the synthesis method. And third and fourth principles, sometimes we call it design for safety itself. So third is design for non-toxic reagents and byproducts itself. So we want to involve synthesis that are using non-toxic reagents and produce byproducts that are not harmful to the environment. And also design of safer chemicals itself, right? For the final products that have similar properties as what we are using today, but is safer to the environment. So we want to work in substance. So we look at safer solvent itself, because most of the solvent that we are using for organic synthesis today, these are organic solvent, and this can be hazardous to the working environment and to the general environments that we live in today. So how can we make use of solvent that are much more safer than the organic solvent itself? So we also want to look at how we can optimize the energy usage so that we can achieve an energy efficiency for the reactions. Then usage of renewable feedstock as far as possible. We also look at direct synthesis, reduce derivative, and also, as mentioned earlier, using catalyst, make use of catalyst to make the synthesis environment milder. Therefore, we can have a more simplified reactions. We can also make use of less energy itself because we do not need to heat up the energy to a much higher extent. And if we are able to use catalysts that are solid, we can do away with separations of the products and catalysts subsequently. And also we want the products to be only available in the environment as long as it is being needed, and therefore the design for degradable products itself. So once the products are no longer used, it should be able to degrade in the environment and become harmless materials in the environment. I also want to have in-situ analysis. We want to know when the reactions gone wrong, so that that can help in terms of control of the waste that is being produced itself, and also the amount of energy that is being used to produce the waste. And also we want to look at safer chemistry because if we are using chemistry that is hazardous, the accident could happen that could lead to loss in life, loss in facilities, and harm to the environment itself. So here, the first principle of green chemistry is prevention. Prevention is again better than cure. We want to prevent the waste being produced rather than treatment of the waste. So it's better to prevent waste than to treat and clean up the waste after it is being formed. So a lot of money has been spent on waste treatment, disposal of it, and in the past this has not always been considered in the cost of plant or what we term as full cost accounting. So today we use the term life cycle analysis itself, and therefore these are important to account for the waste being produced and to account for the cost in terms of waste treatment and disposal. So usually this again will require extra unit operations to clean up the waste after usage itself. So industry mindsets is changing today. So we're always thinking about how to prevent waste and how to minimize pollutions itself. So we can do it via substitutions or solvent that is being used today, or animate to remove toxic intermediates itself, or to create new reaction path or new chemistry so that we can avoid the pathway that is that can lead to byproducts productions and energy wastage of energy itself. And here we are looking again on atom economy. So synthetic method should be designed to maximize the incorporations of all materials in the process into the final products. As far as possible, we try to do that. So for example, for atom economy reactions, again, reaction is 100%. The additions is atom economical because we are adding two reagents together. Substitutions depend on reagent use, but normally one part is being substituted out. That means that a byproduct will definitely be produced. So eliminations reactions, that means that one part of the molecules will be cut off, and therefore that will be a very not atoms economical reactions. Here we look at examples of design for non-toxic reagents and byproducts itself. So we look at wherever practical, synthetic methods should be designed to use and generate substances that possesses little or no toxicity to human health and the environment. So we try to look at chemical processes that will not produce toxic products or byproducts to the environment and to human health as well, and also try to minimize the amount of waste. So example here, we have adipic acid as a starting materials of nylon 6,6 synthesis here. So worldwide industry of industrial adipic acid production was estimated to be about metric tons per year in 1998. So it's mainly produced by nitric acid oxidations or cyclohexanol. So the byproduct is nitrous oxide or N2O. So these are very powerful greenhouse gases. So its global warming potential is about 300 times higher than CO2. So we try to look at how to synthesize the products or avoid such production itself. So here we also look at safer products. So chemical products should be designed to preserve the effectiveness of function while reduce the toxicity. So here, so it's always possible to design safer chemicals through manipulations of the molecular structures now. For example, in the past, thalidomides, we do not understand it. It's being used to prevent morning sickness, but it actually causes birth defect as well. And therefore, we try to produce drugs that are in general safe to the human being. So here, designer should evaluate the inherent nature of the selected materials and energy inputs to ensure that they are as harmless as possible as a first step toward a sustainable products, process, or systems. So the use of other substances, right, such as solvent, separation agents should be made unnecessary wherever possible, because whenever we use of solvent or separation agents, these are not being used in the reactions. These are not going to be end up in the products, and therefore we need to dispose of them eventually, right? So concern for solvents, we can make use of it. For example, looking at supercritical fluids, or look at reactions that do not involve solvents. And if we need solvents, whether we can make use of water as a solvent itself, because it's less harmful than the organic solvents that we are using today, or we, in terms of separation agents, whether we can actually look at solid acid or immobilize these add the catalyst into the solid phases so that we can avoid the separation subsequently between the products and catalysts, for example. So here is an example of using supercritical carbon dioxide. So traditionally, when we try to decaffeinate coffee, so caffeines are being removed with a solvent called methylene chloride itself, and is being suspected as a carcinogen. That means that by having trace amount of this chemical in the coffee that we drink, it can possibly lead to cause of cancer for the human being. So and also, unfortunately, many of these compounds in coffee, as those responsible for flavor and smell, are also soluble in this solvent itself. So in general, it's not a very good solvent, whether it's for human beings, safety of human beings, in terms of health concerns, but it's also for the products as well. So many governments actually tighten the regulations on environmentally hazardous solvents such as methylene chloride, and therefore subsequently new processes need to be developed to decaffeinate coffee for certain markets itself. So supercritical carbon dioxide actually gain popularity because it can be achieved, the condition can be achieved at a relatively mild critical points of about 31 degrees Celsius and 73 atmosphere. And basically carbon dioxide is abundant in the atmosphere. So if you can get these carbon dioxides from the atmosphere, we are actually trying to recycle or reuse the carbon greenhouse gases that we are emitting to the environment. So supercritical solvent can easily remove most of the caffeine out of the raw coffee beans, but it can also it will preserve the aroma of the coffee as well and taste, and therefore subsequently it become a very popular method in terms of decaffeinations of coffee beans. So I'd like to look at the design for energy efficiency. So energy requirement is always required in the manufacturing of products. So these are being recognized for their environmental and economic impact, and we should be minimized because we know that chemical and petroleum industry account for about 50% of the industrial energy usage. So about a quarter of this energy is being used in distillation and drying processes in chemical plant itself. So how energy is being used today is in terms of in chemical plants, in terms of heating, cooling, stirring, distillations, in terms of compression, plumbings, and separation processes as well. It's also being used to heat up reactions so that you can increase the speed and also to control the reactions. So most of the energy supply is through electricity, and these are obtained from power plants, and these power plants normally use natural resources or fossil fuel as the raw materials. So we need to burn coal, oil, or natural gas to obtain the energy, and the end result is, of course, we produce carbon dioxide to the environment, and that lead to global warming. So we need to know how to maximize the usage of energy within the chemical plants or to optimize it so that the product processes and systems should be designed to maximize mass energy space and time efficiency. So here, mass and energy efficiency has become a standard chemical engineering optimization processes. We also look at usage of renewable feedstock itself. So raw materials or feedstock should be renewable rather than depleting. Wherever technically and economically viable itself, we want to make use of renewable versus depleting resources itself. in terms of our synthesis method, we try to have more direct synthesis so that we can reduce the number of steps involved itself, and also the unnecessary degradations, such as looking at blocking groups, protection groups, deprotections, temporary modification of physical chemical processes, which should be avoided where possible because these are additional steps towards the synthesis routes itself. So we also need to take care of the activity and selectivity of the synthesis, because the higher throughput with less waste, you'll need less energy for the productions itself. So here you can try to make use of biotransformations. So active enzyme in nitriles actually help in terms of in these productions, and therefore that lead to less usage of basically chemicals or reagents in the processes. So again, catalysts, we try to look at catalytic reagents, especially selective one, so that we have more of the desired products that we want to. So these are more superior to stoichiometrics reagent as well. So organic synthesis chemistry is slow to adapt to modern development in catalysts. So new routes that can replace inorganic stoichiometric reagents, such as oxidations and reductions. There are new methods to do it. So many published catalytic routes are far more selective and efficient compared to the methods used in traditional organic chemistry, such as using chromium compounds, reductions using various agents itself, and using mineral acids. So today, for example, we can use solid acids to replace mineral acids, and therefore that will help in terms of avoiding the separations of the catalyst and the products subsequently, because the solid acids will not dissolve, will not mix with the products itself. So here we also look at example. So there are Nobel laureates that won Nobel prizes by developing new synthetic routes with catalyst itself. So here, for example, Professor Roberts of California Institute of Technology are able to catalyze ring opening polymerizations of olefins in water itself. You can see that by making use of catalysts, you are able to conduct reactions that is traditionally difficult itself, such as ring opening of hydrocarbons, and also in water now that we can avoid the usage of organic solvents. We also like to look at the final products that are being obtained from the chemical synthesis. So like to design for degradable products itself. So chemical products should be designed so that at the end of the functions, they do not persist in the environment and break down into degradable products at the end itself. So in the past, we can see that pesticides and plastics are actually very stable compounds, and therefore we like to use them because they stay in the environment for a long times itself, and we can continue to make use of that. But basically, we also realize that become very harmful to the environment, especially for plastic that do not degrade itself. So we need to think of how we can put in the design of new chemical products that are degradable, so that when they are beyond their lifespan or usage, basically what happens here is they will be degradable and become less harmful to the environment. We also like to produce analytical tools itself, especially in-situ analysis methods for pollution preventions. So you need to have further developed to allow for real-time in-process monitoring and control prior to the formation of hazardous substance. So we cannot control what we cannot measure. So in this sense, that if we are able to measure what is happening in the reactors, definitely we will be able to control the reactions, and therefore that can help in terms of the control of the formations of hazardous substance. So here we need to know the in terms of the chemical plant processes, We need to change many things, change on processes during operation needed for reliable sensor. We need to monitor the progress of the reactions, and we need new analytical techniques as well, so that we are able to measure what we want to know is happening in the reactors, and therefore able to assess hazard present in the process streams. As we move on, we also want to look at inherently safer chemistry for accident preventions. So substance and the form of a substance used in a chemical process should be chosen so as to minimize the potential of chemical accidents. This includes the release, explosion, and fire to the chemical plants itself that can harm the besides harming the environment, can also lead to the loss of human life. So we need to minimize hazard using processes or equipment design features which reduce frequency or consequences of accidents without the active functioning of any devices. For example, we can use a containment around a hazardous material storage tank. We can control, have safety interlocks, automatic shutdown system itself, can have multiple active elements such as sensor to detect hazardous conditions. We have a logic device to decide what to do and to control elements or implement action. So we can prevent incidents or mitigate the consequence of incident as well. So example, high level alarm in the tank shut automatic defeat valves in the way, so that can lead to a safe process. So there are various examples of this. For example, in a batch chemical reactors, hazard of concern is a runaway reactions causing high temperature and pressure and potential reactor ruptures. So a passive way to solve this problem is to have a maximum adiabatic pressure for reactions determined to be 150 psig. So we can run the reaction in a 250 psig design reactors. So the hazard will still exist, but passively contained by the pressure vessel. So this is one of the passive methods that we can use, or we can have an active way or procedure. So we can maximize adiabatic pressure for 100% reactions at 150 psig. Reactor design pressure is 50 psig. So we can gradually add limiting agent reactants with temperature control to limit potential energy from reactions. So use high temperature and pressure interlocks to stop feedstock from going to the system, and therefore that help to apply emergency cooling as well as a safety measure. So we can provide emergency release systems for such systems itself. It can also be in terms of procedure. This will need some human interface as well. So maximize the adiabatic pressure for 100% reactions in 150 psig. Reactor design pressure is 50 psig. So gradually add limiting reagents with temperature control to limit the potential energy from reactions. So you need to train operators to observe temperature, stop the feedstock, and apply cooling if temperature exceeds critical operating limit here. We can have an inherent processes, so we have to develop chemistry that is not exothermic or mildly exothermic in the process. So maximum adiabatic exotherm temperature is less than boiling point of all ingredients and onset temperature of any decompositions or other reactions, and that can prevent an explosion from occurring. So which strategy should we use? Generally, in order of robustness and reliability is as follows. If you have used the inherent methods, that means that we have removed the hazard totally. For passive, we are over designing it. That means that we are using it as a cost itself, as a high. We need to spend more money to ensure that everything, all the hazard is being contained. Active and procedure are the one that need to also put it in as well. One is through using interlock. The other one is using operators as well, trained operators. But there is also a place and for all these strategies in a complete safety programs in a chemical plants. So with that, what I've covered for today, we look at the 12 principles of green chemistry. So we know that all the 12 of them, prevention is better than cure. We look at atom economy, as long we want to come with reactions that is more atom economical. We want to design for safety, be it in the non-toxic reagents and byproducts as well as the products itself. So we need to design for safer chemicals. We want to work in substance, so we want to avoid the usage of solvent. If not avoidable, how can we look at substance solvent that is less harmful and require less separation processes subsequently. We look to design for energy efficiency itself in the process so that we can minimize the energy use and therefore the emissions of from the power plant side. We need to look at usage of renewable feedstocks itself, how we can make use of renewable resources so that we not be depleting the natural resources. As far as possible, we try to make the synthesis more direct and reduce the number of steps involved, because more steps means that you are using more reagents, producing more waste, and using more energy. And as far as possible, we try to make use of catalysts, as because catalysts most of the time can lead to alternative pathway, and therefore make the reactions condition milder. And also another pathway is to reduce the amount of waste being produced. We need to look at the final products. You need to only be in the environment as long as it's being needed and should be degradable after its usage. We need to have more tools to monitor the reactions in the chemical plants so that we can prevent pollutions or waste from being produced by knowing what we can measure in the chemical plants itself. We need to have inherently safer chemistry to prevent accidents itself in chemical plants itself. You can see that all these 12 principles of green chemistry also sit very nicely into the ideal synthesis model itself with the number that is attached to it. With that, I'll end my lecture today, and we'll take questions from you. Is there questions?
Hello everyone, do you have question? If you have question, please unmute your microphone and can your question. Hello, do you have question, everyone? Okay, I think it's not a question, Mr. Lim. You can continue.
Okay. No questions. Thank you very much once again. And thank you for attending the lectures. Bye-bye.